In this session, I will be talking about compensators and controllers. What I have observed from my experience is that because this is the last portion, by the time this portion is dealt with in the classical control and in your coaching or even in your college, this is the last portion. So people usually tend to ignore it. They will give you some generic forms of lag lead and lag lead compensators without discussing much, without giving you much inputs, and a lot of problems and confusions arise because of that. And where will that reflect? I'll tell you what is happening and why a separate video is being done on this, separate questions are being dealt with it. Is the thing is that for me, my responsibility is that I want to simplify that particular topic for you before the GATE exam. Okay, there are just very simple points that you have to remember. You can solve the question very easily. Okay. Right now you are seeing this particular question on the board. So I will just read this question out. We will see how to solve. Even before that, I will clear most of your confusions. What type of confusions will come, I will tell you. First of all, many people get confused. In lead compensator, the pole zero location, and in the lag compensator, pole zero location, if somebody will suddenly ask you, is the zero leading in the lag compensator or leading in the lead compensator? Is the pole lagging in the lag compensator or leading in the lead compensator? What is it? Such questions will confuse you for starters. Second, not just compensators, there is another topic called controllers also, where PID controllers and all come into picture. Is there a relationship between compensators and controllers? The answer is yes. Okay. Some of the compensators will be equivalent to some controllers. Lag compensator will be equal to some control. Lead compensator will be equal to some control. Lag lead will be equal to some other control. Which is what? Again, confusion will come. Whether lead is like derivative controller, whether lag is like derivative controller, or vice versa. Confusion has again come. Second point. Third point is, in controllers, there is one more thing that comes. Why do we add controllers? Because we feel that either the transient or the steady state response, so all the analysis so far, whatever you did in finding error, in finding transient response of a system, all of that you have done only for one reason, and that reason is that you basically want to fix some problem that is there in the system. Now when it comes to fixing, you should know appropriately which to put, right? Which controller I have to add in that, okay? Whether it is the D controller that will fix the transient, whether I controller will fix the transient, whether I controller will fix the steady state, and vice versa, so and so forth, right? We do not know. Again, confusion is there. Okay, because of to address all of these confusions, I have decided to take a little bit of theory before I get into solving this problem. And I'll promise you one thing, stay tuned till the end of this session. By the time, if you'll remember a couple of points that I'm going to tell you right now, okay, because as I told you previously, I am very forgetful myself. If I am able to remember it till now, I'm very sure you all will be able to definitely remember it for much longer time, okay. Just remembering those points, you'll be able to answer the questions very easily, okay. So let us get to it. Let me just give you a small brief into compensators and controllers. First point that I want to address, first point of confusion, okay, is the location of the poles or zeros. Randomly, if I were to draw the following diagram, okay, so forget the question for now. I am drawing a diagram over here. So the diagram is something like this, okay. This is the S plane, okay. So obviously this has to be sigma and j omega. Never forget these basics, sigma j omega, okay. This is my pole, this is my zero. I will randomly ask you whether this is a lead compensator or a lag compensator. Suddenly the people who are wonderfully feeling easy, control system is easy, we can score full marks, will get caught here. Why they are getting caught? Confusion was there and it was not touched properly, okay. So to remember that, there is a method, okay. We don't like poles very much because poles will induce instability in the system, right? We like zeros a lot. Now whenever you get up in the morning, you would like to see the favorite person first. Okay, let us assume you are standing here. This is the viewer, whoever is seeing this thing. If you are standing over there, the first thing that you are seeing right now is a pole or a zero. It is a pole. Okay, now this is not good. You basically wanted to see a 0. So what is happening here? You will make an English statement. In English, you will make a statement telling that my 0 is lagging the pole, or my 0 is lagging. Whenever such a term comes, because of the 0 being lagged, you will say that that compensator is a lag compensator. So this is a lag compensator. Okay, because you're standing here, you are seeing the pole first. Okay, you wanted the 0 to be leading, but no, this is lagging, right? Because it is coming behind. It is coming behind because of it. This is a lag compensator. What will be my lead compensator? Exactly opposite of this. So I will just write that down over here. So once again, this is my sigma, this is my j omega. All right. So I have it like this. Okay. Once again, here my 0 is there. This is my pole. Here my pole is there over here. This is my 0. And again, I'm standing over here. Here you see what is happening. My 0 is coming first. So this is my lead compensator. First point to remember. This is not the theory. This is just a shortcut to remember lag and lead compensator. Many people may say this is very trivial. Let us come to the next part. Lead compensator will mimic one of the controllers. Is it P? Is it I? Is it D? Is it PID? I want to know. For sure, one obvious thing where everybody will answer is lag lead compensator that is there. Lag lead compensator is like PID controller, they say. That is obvious because obviously both combinations are there. The confusion will come, is this equal to a PI controller? Is this equal to a PI controller? Is this equal to a PD controller? Or is this equal to a PD controller? Now to solve that confusion, you don't have to remember any technical knowledge or anything like that. Trust me, you have to just remember one thing. Okay, look at the spelling of lead. What is the spelling of lead? The spelling of lead is L-E-A-D, right? Because this is the spelling of lead, I apologize, I just have to fix my mic, right? So because this is the spelling of lead, you see the D is over here, this is like the PD controller. Right? Very simple to remember. You can never forget this. This is nothing but like the PD controller. Lead compensator is nothing but a PD controller. So because this is PD controller, this has to be a PI controller. Right? Second confusion solved. What is the second confusion? You people wanted to know lead is a PD controller or lag is a PD controller. Solved. You know what is pole 0 location. Why am I telling this? All this may be sounding very trivial, but when we will solve some problems, you will understand that directly, because knowing of these small tips, you will be able to get the right answer within minutes. Okay. Next point. Next point is which one will fix what? PI controller, will it fix steady state error or transient response? PD controller, will it fix transient response or steady state error? For that, very simple, again go back to English. See, you all are having English in your GATE exam syllabus. Okay, why it is important is many things can come from there itself. All those terminologies in English only we have bought here in control and using it, right? So why I am telling you to go back to English is it's very simple. See, most of the times you might have heard of the statement telling that I have done some original work, but my friend has derived his work from mine. What I mean by that English statement? Some other person to get into the market immediately has copied you. He has no original idea. He has derived it from you. Okay, to get into the market immediately. What I mean by getting into the market immediately, to fix his transient response, immediate response, he has tried to use the derived work. So in short, what I want to say, because this is a derivative controller, it will give you the essence or a sense of fixing your transient response. So your PD controller will be responsible for fixing your transient behavior. Okay, don't mind my handwriting. So transient behavior. Alright, so PD controllers are responsible for transient behavior. Again, PI controllers will obviously, if this is there, this has to be there. So there is an English statement for this also. You are basically trying to do new research. So what you are doing, you are integrating many works. You are taking his work, everybody's. You are trying to build a novel theory. That time what will happen? You will become sluggish. Right, you will take time to publish your work, right? You are becoming sluggish, but what will happen at the end? Your work will be very much noted. They will say that his work is proper, his or her work is best, there is no error whatsoever, right? Because you took time in integrating everybody's work and coming up with a new idea. So PI controller will be definitely responsible for fixing your steady state error. Okay, so steady state error. Okay, only 3 points. This is all. You can write points to remember over here, and remember only this much. You will be able to solve any of the untrivial questions in compensator. Ideally, compensator question should be like this. They'll give you the compensator equation. They'll ask you where is the maximum phase shift, what is the gain, what is the cutoff frequency in Bode plot. All of those things are very trivial questions. Non-trivial questions are the types that I am about to solve now in this session. You will get to know that using only these three, I will not erase this at all. This will be there on the board itself. I will show you using only the knowledge that I have got from this, I will solve all the questions. For starters, let us start with this question. A double integrator plant or a system has the following transfer function: k by s square, h of s is 1. E is to be compensated to achieve the damping ratio eta equals 0.5 and an underdamped natural frequency omega n 5 radians per second. Which of the following compensators GC will be suitable for the job? Okay, first thing what you have to do over here, he has given you the feed forward gain, he has given you the feedback gain. Okay, find the overall transfer function. Okay, so I will just solve it over here because I don't want to erase that. So I will just make a small division over here. I am solving it over here. Okay, so overall transfer function currently will be G by 1 plus GH. So that is nothing but I have K by K plus S square. Okay, now if you see this particular transfer function, you will understand the following thing. Okay, if you take Laplace inverse of this, very simple, take Laplace inverse of this. That is nothing but the impulse response. What is it? It's a sinusoidal waveform, right? What I mean by sinusoidal waveform means when you take Laplace inverse of this, you are basically getting impulse response of the system. Impulse response, when you are giving an impulse input to the system, this particular system currently is generating sinusoidal output. So the output is bounded, which means that what has happened, it is nothing to do with the sort of error or instability, no problem of that sort is there. It's just that its transient behavior is affected. That means that its damping ratio is 0. Currently the damping ratio is 0. We want damping parameter to come as 0.5 and omega n to be 5 radians per second, right? So because this is a transient behavior that I have to fix, transient behavior is what I have to fix for this particular question, and from the shortcut you know transient behavior will be solved by PD controller, and D controller is nothing but lead, D is their lead. So I have to see a lead transfer function here. Which of these transfer functions are lead? How to know? You plot the pole 0 locations for each. What should happen? I know in lead my 0 should be leading. In other words, the magnitude of my 0 should be smaller because obviously it is here. Magnitude of the 0 should be smaller as compared to the pole. So let us see, is this a viable answer or not? We will see. Yes, this is a viable answer. Obviously, my pole is back, my 0 is leading. This is a viable answer. Now this particular thing, let us see, this is not a viable answer. Is this a viable answer? Actually yes, this is a viable answer, but this is unstable because there is s minus 6 that is coming into the picture. This is unstable. This cannot be a viable answer. Now this particular thing, let us see. This particular thing, what is happening? You are having a 0, you are having a pole at 0 and your 0 at minus 6. That is not a lead compensator, that's a lag compensator. So your correct answer, because you are trying to fix the transient, your correct answer should be option A. Now let us see another interesting question. Let us look at this question again on compensators and controllers. So if you read this question very carefully, let us read this question first of all. A unity negative feedback closed loop system has a plant with the transfer function g of s equals 1 by s square plus 2s plus 2 and a controller g of s, gc of s in the feed forward path. Okay, so there is a controller. Okay, for a unit step input, the transfer function of the controller gives minimum steady state error. Okay, and he is basically asking us that what should be my GC out of this so that I get minimum steady state error. Now before you take a pencil and all and start getting all mathematical, learn how to observe some key points. Okay, first of all, whenever controller and compensator question comes, no, highlight what they want you to do with the controller or compensator. What have they asked? They want to basically fix steady state error is what they want you to fix. Because you have to fix steady state error, two possibilities will be there. Either you can use PID controller or you should be able to use some other controller. What is that steady state error? See the shortcut PI controller, you should be in a position to use. Any one of these controllers you should use. Why not PID? I will tell you. PID will fix transient as well as steady state. Okay, but there should be something to fix in the transient. No, this is the system. This is a second order system. This is a underdamped second order system, if you will see. So its transient behavior is already fine. Only steady state error is coming. Because of that, I don't have to use PID. So by default, if you look at the option, this is a PID controller, eliminated. This is a lag lead compensator, which is a PID controller, eliminated. Out of these two, I want to choose PI controller. By the shortcut, lead is PD because D is there. So lag has to be PI. Out of these two, which is the lag thing is what I have to see. In a lag, what should happen? This is the diagram. So my 0 should come last. My pole should come first. So the pole magnitude must be lesser than the 0 magnitude. My pole magnitude must be lesser than my 0 magnitude. So option B is right. You don't have to use any mathematics to solve this question. Alright. Now let us see another interesting question. So this question always brings a smile on my face because this is a very good question and this is actual control. Basically this particular question, if you are able to solve or anything like that, no, this is what we do. Okay, we as researchers apply one concept to another and try to get the answer. We will see what I mean by that. You will get a small flavor of that here, and this is a GATE question. Okay, this is what GATE is all about. So pay a lot of attention to this. Okay. So I have saved the best for the last. So this is the best question that I have. Okay, that was asked. Okay, let us read the question very carefully and understand what it is. The open loop transfer function of a plant is given by g of s equals 1 divided by s square minus 1. S square minus 1. If the plant is operated in a unity feedback configuration, if nothing is mentioned, it is negative feedback only. Please do not think otherwise. Feedback configuration, then the lead compensator that stabilizes the closed loop system is, first, he has clearly told it should be a lead compensator. It is not your choice. Okay, it is not your choice to put any compensator. Even if it was, ideally you should put a lead compensator itself, but that comes in deep analysis and control system design, which is not a part of your syllabus. So you see, this is very well tailored GATE question. They know that is not in your syllabus, and they know that if they will not give this portion, lead compensator, problems will happen. Many people will not be able to solve. To ease that, they have already given that it should be a lead compensator for starters. Second, the transfer function is 1 by s square minus 1. S plus 1 into s minus 1. So there is definitely a pole on the right hand side. This is an unstable system. Okay, because of which, now I will tell you how I told you in deep analysis this lead compensator is there. If it was not there also, you can come to know, because what is happening, because it is 1 divided by s square minus 1, the moment it is an unstable system, no, the transient behavior is what you will try to fix first. Always. Then you will worry about steady state. See, error and all comes to a stable system. If you are not stable itself, first I have to try to stabilize you and bind you, right? So always when an unstable system is there, you will either try to develop a PD type of a controller. That is nothing but a lead compensator. Okay, that's the reason very mathematically he has given lead compensator. First of all, let us try to isolate which of this is a lead compensator. Okay, let us see this. Okay, let us see the first option. 1 is there, okay, that is nothing but the 0 minus 2. Definitely, if you were to stand here or anywhere, the 0 is either behind you or in front of you, that is lead. Okay, pole is lagging, this is a lead compensator. But is this a lead compensator or not? I will tell you. The problem is this is unstable. You cannot design this. This is not a design, this is nothing, this is improper. So this is not a correct answer at all, rejected. See, one may feel that by putting this here, just beside it, you are able to cancel this and the unstable pole 0 cancellation is happening. Many people who overthink the question will feel that, but it is not the right way to design. To cancel an unstable pole of a system, you cannot add an unstable 0 to that. No, that is improper, that is illegal. Mind you, I am stressing it many times. So this is not the right answer. This is not an option at all. Eliminated. Okay, so eliminated. Is this a lead compensator? If you see in a lead compensator, what should happen? Magnitude of the 0 should be less than that of the pole. Magnitude of the 0 is 4, magnitude of the pole is 2. No, this is a lag compensator. This is not correct. Is this a lead compensator? Yes. Is this a lead compensator? Yes. Now the problem is, now you are stuck. Now what to do? Two correct answer is not there. There is only one correct answer for it. You may feel that there are two, but no, it's only one. How to choose between these two, I will tell you. What has happened? This is your question. The only difference in these two is the gain. Let us assume that gain as k. Okay, we have assumed the gain as k. I will start solving over here. Let me make a small partition. Okay, I will assume the gain as k. Let me assume the same pole and 0. So my compensator for now, I have selected among the options as k into s plus 2 by s plus 10. I selected it. My system g of s 1 by s square minus 1. H of s is unity feedback. Okay. The loop gain or the characteristic, if I want to find characteristic equation, that is 1 plus g of s h of s, correct? Because it is 1 plus g of s h of s and even gc is there, it will be 1 plus gc g h of s. Because of that, my characteristic equation now will be what? 1 plus k times s plus 2 by s square minus 1 into s plus 10. This is the characteristic equation. Okay, you want to put equal to 0, put equal to 0. Now, you know, many people, the moment some question comes, what is the range of k for which system will be stable? People will take pen and immediately jump into it by applying Rautherwitz criteria. This question is actually Rautherwitz criteria, indirectly asked to you, but nobody will find that out because people know how to apply Rautherwitz criteria. Everybody knows. But what they don't know is when to apply where. Now you see what I have to do. I have to find out the Raut array for this and find the value of k that will make the system stable. Okay. So let me quickly do the Raut array. So I will erase this shortcut because this is the last problem I will be handling. So let me just erase this. Points to remember. I hope you have all noted this down. This is very essential. You will not get these points directly. So out of lot of experience I have written these points. This should be sufficient. This should suffice for any other problem. So let me quickly make Raut array for this and choose between option C and D. Okay. So what will I get? Let me just write over here. Okay. So I am having s square minus 1 into s plus 10. Okay. Plus k into s plus 2 equals 0. Okay, so very quickly let me just multiply it. I have s is cubed over here, okay, minus s plus 10s squared minus 10 plus ks plus 2k equals to 0. Okay, cubic polynomial. So I have already solved this in my book. So I will just write down the Raut array for you. Okay, so if by chance you were to simplify this, you will get the Raut array in this manner. I don't want to take much of your time since all of you are preparing for the exam. So this is this type of array you will get. So what will you have? You will have 1, k minus 1, then you have 10, then you have 2k minus 10. And always to check if your Raut array is correct or not, after you get this polynomial, no, your last term should be the last term over here. If that is not happening, you have done some mistake in your Raut array. Always remember that. Okay, the last term of your characteristic equation should be the last term in the Raut array. Here the last term will be the constant value, that is 2k and minus 10. So I have to definitely get a 2k minus 10 over here, no matter what. Okay, this particular term we will see how I do. If whenever I am going up, see, whenever anybody goes up in life, no, people will be jealous of him. Okay, so multiply this. Okay, and then you have to subtract the ideally you have to subtract the thing that is coming down. Okay, that is the actual procedure. So that is what I am going to do. let me take this minus this, or either ways, so you can do this. So k minus 1 minus, so you have 2k minus 10, the whole thing divided by 10. Okay, now what will happen, you will see that the constant 10 into minus 1 is there, this you are getting plus 10, so the 10 is getting eliminated. So in short, this first of all, for stability, all of this value should be greater than 0. Okay, for k to be greater than 0, here obviously you will get k to be greater than 0 in this inequality. Here you will get k to be greater than 5 if you solve it. If this has to be greater than 0, k should be greater than 5. Because k should be greater than 5, from here, which of the two options are correct? Is this correct? No, because k is less than 5. Is this correct? Yes, this is the most correct answer. This is correct. This is how you have applied the logic of Rauterwitz criteria in developing a controller for your unstable system that was here. In short, you have also fixed its transient response. And ideally, if you are a good design control engineer, okay, in your masters you will learn that after you have designed that, you will check the steady state error, then you will try to appropriately develop something more, and then on you will keep designing in that manner. Okay, with that, controller compensators, challenging questions that are good questions asked in GATE, I have covered most of it. Some more doubts are there, please send in all your inquiries via mail. I will be happy to answer with lot of easy shortcuts. I will explain it to you, nothing to worry. And with that, I would like to conclude this session, and very all the best for your exams. Stay tuned for some more videos. Thank you.